Suppose now we have a 15 kilogram object with a 26 Newton force on it, and this force acts for a time interval of 10 seconds. What is the acceleration of the 15 kilogram object, and what's the change in velocity over the 10-second time interval? The acceleration of the object is just the force divided by the mass, and that's the 26 newtons divided by the 15 kilograms, which is 1.7 meters per second squared. Recalling that a newton is a kilogram times a meter per second squared, a unit of force times a unit of acceleration, unit of mass times a unit of acceleration. Excuse me. When we divide by the unit of mass, we end up with simply the unit of acceleration. So the change in velocity is approximately 1.7 meters per second squared times the 10 seconds. The 1.7 meters per second squared is the approximate acceleration. Actually, it's 1.7333 repeating threes. But just making this approximation, the change of velocity will be the approximate acceleration times the 10 seconds, or 17 meters per second. Now let's just note something about this situation. The distance that we travel in the 10 seconds, of course, depends on our initial velocity. So that if we wanted to calculate the work done by this force, we would have to know the initial velocity, because the initial velocity and the change in velocity will give us our average velocity, which then multiplied by the 10 seconds will give us the distance. And in order to calculate the work, we have to multiply the force by the displacement. So our delta W, the work done, depends on the initial velocity. The greater the initial velocity, the more work is done. In next situation, let's say that we have a 5.3 kilogram object and a net force of 21.2 newtons is exerted on the object. Now this is the net force, the sum total of all forces. If we're pulling on it and friction is dragging and the wind is, we've got a tailwind, let's say, that's blowing the thing forward, we add up all those forces and we get the net force. Okay? And that's 21.2 newtons. We assume that the object starts from rest, and we look at what happens for a time interval of 2.3 seconds. What we want to do is find the acceleration, the final velocity, and the displacement. Well, the acceleration, again, is just the force divided by the mass, 21.2 newtons over 5.3 kilograms, which is 21.3 kilogram meters per second squared, divided by the 5 kilograms, and we end up with 4 meters per second squared here and here. So our delta V, change in velocity, will be the 4 meters per second squared acceleration multiplied by the 2.3 seconds, or 9.2 meters per second. The average velocity will then be the average of the initial and final velocities. Initial velocity 0, final velocity 9.2 meters per second. We divide that by 2. We get our 4.6 meters per second. So our displacement will be the product of the average velocity and the time interval, the 4.6 meters per second, the 2.3 seconds, or 10.6 meters. Fairly straightforward calculation once we find our acceleration. Note now that if we wanted to, we could go on and find the work done. We know the displacement, we know the force. Okay, so we could find the work done by the net force. And of course, if we know the work done by the net force, that is the kinetic energy change. So knowing the kinetic energy change, since the object started at rest, it had 0 kinetic energy. The change in kinetic energy then just equals the final kinetic energy. So we know the mass and the 1/2 mvf squared, the final kinetic energy. We could solve this, then to find Vf, and we'll do that in later problems. Now to diagram the process, what were we given? We were given net force, mass, delta T. We were also given that the initial velocity was 0. What can we find? Well, from the net force and the mass, we can find the acceleration. From the acceleration and the delta t, we can find the change in velocity. From the change in velocity and the initial velocity, we find the average velocity, and then from the average velocity and the time interval, we can find our displacement. That's what that was our task for this problem. Now, having the displacement, we could put that together with the net force and get the work, which would be the final kinetic energy, the change in kinetic energy, and therefore the final, and so on. If we have an 88 kilogram mass moving at 11 meters per second, what's its kinetic energy? And what's its kinetic energy if the velocity doubles? And I think we also want to find here the ratio of the kinetic energies, the original and the kinetic energy if the velocity doubles. Well, kinetic energy is defined as 1/2 mv squared, which will be 1/2 of your 88 kilograms times your 11 meters per second quantity squared, and that comes out to 5,324 joules. The units, we have kilogram meter squared per second squared. Okay, and that's a kilogram meter per second squared times a meter, which is a newton, times a meter, which is a joule. Now, if the velocity is doubled, the kinetic energy will become 1/2 m times 2v squared, where 2v is the new velocity. And that could be calculated to be 2 mv squared, but really what we want to do is go on and find the kinetic energy ratio, the new kinetic energy over the old. Well, this is the new, this is the old. The 1/2 m's divide out, leaving us 2v quantity squared over v squared, which is just 2v over v quantity squared. The v's divide out, and we end up with 2 squared, or 4. So we have 4 times the kinetic energy if we double the velocity. Okay, this is something that should make an impression on you. Doubling the velocity doesn't double the kinetic energy. If you increase the velocity, it increases the kinetic energy, but if the velocity doubles, the kinetic energy increases by a factor of 4. And we've just proved that result.